Welcome to this explainer. Look, if you've been tracking the EV space at all, you already know lithium is the undisputed king of the battery world. But what you might not know is that the way we actually extract and refine this critical element, it is quietly undergoing an absolute high-tech revolution right under our noses. We're going to dive into exactly why powering our low-carbon future requires a massive overhaul of how we get our lithium. 12 to 24 months. Think about that for a second. That is currently how long it takes to slowly evaporate and extract lithium from traditional solar ponds. In an era where global demand for EVs and grid storage is just exploding, we are literally waiting up to 2 years for the sun to do its job. It's a pace that simply cannot keep up with a fast-moving energy transition. And these operations are just colossal. They eat up massive amounts of land and water in some of the most arid regions on the planet, places like the Lithium Triangle in South America. So while the resource itself is abundant down there, this specific extraction method places an enormous strain on local ecosystems. It's acting as this massive, environmentally damaging bottleneck for the entire global EV revolution. So here is our roadmap for today. 1. The refining bottleneck. 2. The electrolysis solution. 3. Upgrading hard rock. 4. Brine and DLE. 5. Closing the recycling loop. And finally 6. Real-world proof. Section 1. The refining bottleneck. Let's establish exactly why our current methods are simply unsustainable. Okay, so the dirty truth of conventional refining is pretty staggering. When we look at traditional processing, especially for hard rock deposits, which actually make up about 60% of our global supply right now, it requires incredibly intensive chemical leaching. This old-school chemistry creates 2 tons of useless toxic sodium sulfate waste for every single ton of lithium produced, 2 to 1. It has basically no commercial value, and because it's highly soluble, it easily leaches into groundwater, messing up soil and aquatic life. It's such a massive liability that a Finnish court recently blocked the opening of a major battery materials plant purely over concerns about their plan to discharge this sodium sulfate wastewater. Section 2. The electrolysis solution. The silver bullet to this massive waste problem. The beautiful thing here is that we really don't need to reinvent the wheel. We are borrowing a proven trick straight from the chlor-alkali industry, electrolysis. Instead of dumping in heavy chemical additives, electrolysis intelligently uses electrical currents to cleanly drive the chemical reactions we need to produce battery-grade lithium hydroxide. This tech has been safely operating at massive commercial scales since the 1970s for things like chlorine and hydrogen. Now, engineers are aiming that exact same electrochemical principle directly at lithium. Whether we're talking about a 2-compartment or a 3-compartment setup, think of these cells as incredibly smart chemical traffic cops. They take simple inputs, like brine and water, and use selective membranes and electrical currents to pull the lithium ions exactly where we want them. You get a high-purity lithium hydroxide solution on one side and highly valuable reusable acids on the other. All of this without needing to haul in truckloads of harsh, single-use reagents. Section 3. Upgrading hard rock. Let's look at how this applies to our biggest current lithium source. As we noted, hard rock spodumene is huge right now because you can bring a mine online way faster than you can build a massive solar pond. But the traditional way of processing it is brutally energy and chemical intensive. You're mining, doing an extreme acid roast at around 1,000 degrees Celsius, and then running a highly complex chemical conversion using sodium carbonate and lime. In that final conversion stage, that is exactly the step that spits out all that problematic, ecosystem-destroying sodium sulfate waste we were just talking about. But here is the real game changer. If we just slot electrolysis in downstream right after the leaching phase, we completely bypass that old, dirty chemical conversion step. By feeding purified lithium sulfate directly into our electrolyzer, we generate high-purity lithium directly and produce absolutely zero sodium sulfate waste. None. It streamlines the whole facility and radically shrinks the environmental footprint, all while delivering a superior battery-grade product. Section 4. Brine and DLE. Now the story gets even more fascinating when we apply this to underground desert brines. This is where we finally say goodbye to those massive 2-year evaporation ponds. The industry is rapidly shifting to direct lithium extraction, or DLE. Basically, DLE acts like a highly selective sponge that pulls lithium out in mere hours or days. We're talking recovery rates above 80%, which totally blows solar evaporation out of the water. And crucially, it operates in a closed loop. The spent, lithium-depleted brine just gets safely re-injected right back underground, leaving the local water table and the whole arid ecosystem completely undisturbed. And when you pair DLE with electrolysis, it's brilliant. You get this true closed-loop synergy. The DLE process hands over purified lithium chloride to the electrolyzer. The electrolyzer uses electricity to convert that into our final battery-grade lithium hydroxide, right? But during that process, it also off-gases hydrogen and chlorine. Well, those gases are immediately grabbed, synthesized into hydrochloric acid, and fed right back into the front of the DLE process to strip even more lithium. The waste from one step literally becomes the vital fuel for the other. It massively drops operating costs and pretty much eliminates outside chemical dependency. Section 5, closing the recycling loop, because we definitely can't just mine our way to a green future. Regulators are already forcing the industry's hand here, which is a good thing. With strict new mandates rolling out, like the European Union demanding up to 80% lithium recovery from end-of-life batteries by 2031, we desperately need hyper-efficient ways to process what the industry calls black mass. That's basically the shredded guts of spent batteries, and getting pure lithium back out of that complex chemical soup is no easy feat. So, in a modern recycling plant, you dissolve that black mass in acid. Once you filter out metals like cobalt, nickel, and manganese, you're left with a lithium sulfate solution. Just like we saw with the hard rock process, electrolysis steps in. It takes that recovered lithium sulfate and efficiently zaps it right back into battery-grade lithium hydroxide. The leftover acid gets looped back to the start to dissolve the next batch of batteries. It perfectly closes the circular economy loop. Clean, efficient, and deeply sustainable. Section 6, real-world proof, because seeing is believing. I want to make sure it's absolutely clear. This isn't just theoretical chemistry living on a whiteboard. This hardware is actively operating right now. Nemaska Lithium up in Canada brought a massive demonstration plant online way back in 2017. They have repeatedly proven the tech works on hard rock and recycled salts, giving engineers a goldmine of real-world data. Meanwhile, Vulcan Energy in Germany just flipped the switch on their DLA2 electrolysis plant, and within 2 months, by January 2025, they successfully produced battery-grade lithium directly from deep geothermal brine. The technology is de-risked, it's mature, and it is actively scaling up as we speak. By replacing slow, wasteful chemistry with smart, closed-loop electrolysis, we finally have a lithium extraction method that is exactly as clean and efficient as the electric vehicles it's meant to power. The tech is ready, which leaves us with one final urgent question to chew on. Can we truly claim to be powering a green transition if we keep relying on dirty extraction? Thanks for joining me on this explainer, and I'll leave you to think on that.